Okay, class, today we're in lesson 2.4. Lesson 2.4, operations with scientific notations. Operation with scientific notation. Adding and subtracting with scientific notation. Numbers in scientific notation can be added or subtracted, either directly or by rewriting them in standard notation.
Hey, I want to show you that you can actually think about things scientifically using scientific notation. Let's take a look at the solar system and take a look at this question. Find the approximate combined mass of Venus and Mercury, and let's write that answer in scientific notation. Combined mass. Now here's a chart of the masses of all the planets, planet and the approximate mass, and I want to find combined mass. That is a math speak thing of saying adding. So I want to add up the mass of Mercury and of Venus. Oh, they're right here. Boom. So I want to take those two values and I just want to add them up. So I just want to add up those two values. So how do you add up those two values? No, here it is right here, in fact. I don't even like that. Well, okay, I can write it this way. It's done. This is a nice little placard. I guess I would have written it this way because it's the chart. But anyway, it doesn't matter because, of course, addition is commutative. So the order doesn't make a difference, right? You can add either way. It doesn't matter. The tricky thing here is that you just, the temptation is just to start adding, right? But you've got to make sure that in some sense the units are the same. Now they're both kilograms, but the real units are this. This is written in 10 to the 24 kilograms. This is written in 10 to the 23 kilograms. They're not actually the same. So I can't just add these guys, even though you're tempted. Oh, I want to do it. Don't. What we first have to do is make sure these units are the same. In particular, make sure we have the same powers of 10. So we're going to actually pull these numbers out of scientific notation to actually answer the question and find the sum. So how do I do that? Well, what I have to do is, I'm just going to rewrite things here. I've got to write this number as 10 to the 23rd. And the way I'm going to write this as 10 to the 23rd is by thinking about 10 to the 24th as 10 times 10 to the 23rd. Right, 10 to the 24th is just 10 times 10 to the 23rd, after all. And then 10 times this number just slides the decimal over one space over. So I got to be really careful with where I write things. So if I slide this decimal point over one unit to the right, it becomes a 48. And remember, you always align the decimal points. So I've got to write the 48 out here like that, aligning up the decimal points. And then notice that I have a 7 dangling there. Don't forget about the 7 dangling. And that would be times 10. And since I peeled off one of these 10s, I'm only left with 23 of them. And now check it out. Now the units are actually the same. Here I've got something times 10 to the 23 kilograms, and here I've got something times 10 to the 23 kilograms. And now, by adding, I can actually now add as you would like. Remembering where the decimal is, it's very important. The decimal location is going to give me all the answers of the world, or in this case, of the solar system. So let's give this a shot and see if we can do this. If we were to add this right now, what would we get? Well, what's really going on here, in fact, is the distributive property, if you will. Because since this is 10 to the 23 kilograms, and this is 10 to the 23 kilograms, and they're being multiplied, I can factor them out and then just add the stuff that remains. So this really is a tiny distributive property incognito. So I'm going to factor it out right now. 10 to the 23rd kilograms times the sum of these guys. And so what's that? Well, now I add, and decimal points here, so I've got a 0, 7 and 3 is a 0, and I'm going to carry up a 1 in the unit spot, 8, 9, 10, 11, 12, so I got a 2, carry a 1, and so I see a 5. And so I see that the sum is actually 52, actually it's 0.0, so 52 times 10 to the 23 kilograms. Now, of course, I want to write this in scientific notation, and now I've got to translate back into scientific notation. How do I do that? I'm going to write that as 5.2 times, and what? Well, times 10 to the 24th kilograms. Because to slide this over to here, I'm going to actually have to, to put it from here to here, I've got to move that decimal 1 over, which means I need an extra power of 10 to slide that over to here, and so that gives me a 10 to the 24th. So now it's in scientific notation, but notice how we had to get out of it to get like terms. Let's try one more, because that's so tricky. It's tricky, right? Because you're tempted to do certain things, and you can't do certain things. Please. All right. The mass of the moon is about 7.35 times 10 to the 22 kilograms. Question is, how much greater is the mass of Earth than the mass of the moon? Now, how much greater is basically asking us to subtract, to look for the difference, And of course, we're always going to write our answer in scientific notation. So, what do I have to do? Well, here's the mass of the Earth. It's right here, 5.97 times 10 to the 24th. We're given the mass of the moon is 7.35 times 10 to the 22nd. So I want to subtract those two things. So I really want to look at this question. What is the difference between 5.97 times 10 to the 24th kilograms, the mass of the Earth, and the mass of the moon, which is written right down here? So how would I actually combine these? I'm subtracting. Again, the temptation is to just subtract right from here. But you have to get the like terms here. And if you look at this, if you subtract here, you know, the answer is going to be some kind of negative number, and really complicated. But look, this is telling you this is a lot bigger than this. So really, this should actually have a nice positive answer. And so how should we think about that? We have to get like terms. What are the like terms? They're going to be writing everything in terms of the smallest power of 10, which is in this case 10 to the 22. So let's think about this now. I keep this as it is, but I want to convert this to 10 to the 22. Well, that's actually going to be what? Well, it's going to be 10 to the squared power times 10 to the 22 power. So basically, I have to peel off 2 powers of 10. So that's going to be 10 times 10 times 10 to the 22nd power. So if I put in the 10 to the 22nd power here, I now owe you 2 factors of 10, because it's 24 and now it's only 22. I'm missing 2 factors of 10. And what am I going to do? I'm going to eat that up with the decimal point. 1 factor of 10 moves decimal to the right 1 unit, and then the other one moves it to the other unit. So now I'm at 597 times 10 to the 22, and that decimal point, though, has to align perfectly with the decimal point here. So we have this number here, 597, and these are actual invisible zeros here, I guess. And now we subtract. And so now subtracting, of course, you just subtract as always. We'd have to do some borrowing and whatnot. And we see 589.65 times 10 to the 22 kilograms. Again, it's an invisible distributive property. Do you see it? Because this is a common factor. If I factor it out, then what's left over is this difference, and I can compute that difference now. So it really is an invisible distributive property, which is absolutely cool. Now, am I done? Well, it's the correct answer, but it's not written in the nicest form. I really want to write this in scientific notation. So let's do it together. I want to write this in scientific notation, which would be 5.8965 times 10 to the what? Well, what do I have to put on here so that it ends up actually equaling that? Well, what I've got to do, of course, is I've got to up the exponent. So I've got to up it one spot to slide it over that one place, and then another spot to slide over the other place to get to here. So that's 2 moves. That's 2 extra powers of 10 I need, which would be 2, not to the 22, but I add 2 to that, which would be 2 to the 24. And so that is actually the correct difference in masses written in scientific notation. So scientific notation is a powerful way of expressing really, really large numbers or really, really small numbers, and we can combine them by thinking about the powers of 10 and getting those numbers in like terms. And then we can combine, meaning adding or subtracting as necessary. And then we can take the answer and then rewrite that answer in scientific notation. Great. Scientific notation is all over. It allows us to understand not only science, but everything that's big and small. I'll see you soon.
Okay, make sure you write down the key objectives for this lesson. Learn to operate with scientific notation in real-world situations. Okay, multiplying and dividing with scientific notation. Numbers in scientific notation can be multiplied and divided directly by using properties of exponents. Once again, numbers in scientific notation can be multiplied and divided directly by using properties of exponents.
Look at this. Isn't this a great night? Look at that. Look at those planets moving around. Oh my. Shooting star. Wow. You know, I've got to tell you that the solar system is just really a playground for scientific investigation. And there's so many questions that we can ask about the different planets. And I want to actually show you how we can actually understand the planets better. Check out this interesting challenge for us. Here's a question. About how many times greater is the mass of Saturn than the mass of Earth? How many times greater is the mass of Saturn than the mass of Earth? And our challenge is to see if we can write that answer in scientific notation. So here is actually a chart which presents the mass of the planets in the solar system. Here's the planet, here's the approximate mass of Mercury, Venus, and so forth. And now the question is, we want to take a look at the ratio. We want to compare how many times greater the mass of Saturn than the mass of Earth. So the mass of Saturn is here, and the mass of Earth is here. And so we want to look at the ratio of the mass of Saturn, which is this number, 5.69 times 10 to the 26 kilograms, and look at that with respect to the ratio of the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. And so now the question really evolves to, what does this ratio equal? Now, it's written in scientific notation. So what do we do? Well, what we can do here is literally, since there's multiplication going on here, we can actually consider each of these separately. So what I'm going to do is I'm actually going to look at 5.69 divided by 5.97, and then I'm going to look at 10 to the 26 divided by 10 to the 24th. This will involve actually a calculator. So we'll actually have to use a calculator for this one. And so what would the answer be? Well, 5.96 divided by 5.69 divided by 5.97 is equal to 0.9531 and so forth. Keeps going. So I should put approximately. Now, what about this? Now, this is one that we don't need a calculator for, because since this is a power of 10 and this is a power of 10, all we have to do is subtract the exponents. Take the top exponent, the exponent in the numerator, and subtract off the exponent in the denominator. So 10 to the 26, and I divide by 10 to the 24th, I'm left with 10 to what power? Well, 10 to the 26 minus 24, which is 2. And what about the kilograms? The units, notice, they cancel as well. So in fact, this is going to be unit free, which is correct, because it's how many times greater is the mass of one thing to the other thing. So that should just be a number. It shouldn't have units. So notice that the math works out beautifully if you're really careful. Even the units go away as they should. So that is the answer. Now, it's not written in scientific notation. I want this number to be between, 1 and 9, something. So not great. So I need to slide this decimal over. I'd like to do a little slide. A little slide the decimal over here, which would involve me actually doing what? Well, it would involve me actually eating up one of the two factors of 10 I have here. If I remove one of those factors of 10, so I only have one of them now, and multiply this by that 10, it slides over. And so, in fact, what I see here is I could write this as 9.531 something times 10 to the first power. And see, I move the decimal over 1 unit to the right by using one of the two factors of 10 I have here. And now this is in scientific notation. So that's how much bigger, in fact, how many more times greater the mass of Saturn is than the mass of Earth. Isn't that cool? Very, very cool. So just the power of these things. Scientific notation.